Hello everyone, my name is Raph and welcome to my Capstone project. So what I'm going to do in this project is I'm going to be teaching some Chemistry 12 and possibly some pre-calc 12 topics from the BC curriculum. And hopefully my videos can help some of you guys out. And yeah, enjoy. Alright, so my first video will be on reaction kinetics. So let's get started. So what this is the study of the rate of chemical reactions, as well as the factors that influence these rates, and also reaction mechanisms. So when you think of the term reaction rates, like what do you think that means? So if you think of the word rate, that's like something like in respect to time, right? So how long does it take for something to happen? So we know that in a chemical reaction, we have reactants, which then become products, right? So the rate of the reaction can be defined as how fast the reactants are being used up or how fast the products are being made. So let's do an example. All right, so look at this example. What is the reaction rate of disappearance of an excess amount of hydrogen gas when it reacts with 4.5 moles of carbon monoxide gas in 15 seconds to form methanol? So the first thing we should do is to always write the balanced equation. So it says that we're reacting carbon monoxide, so that's CO, and hydrogen gas, H2, to form methanol. So that's CH3OH. Okay, so looking at this, we see we have 4 hydrogens on the right side, so 3 and 1, so that's 4. And the left side we only have 2. So to balance this, we need to put a coefficient of 2 in front of the H2, and then we should be good to go. Okay, so what this problem tells us is that 4.5 moles of carbon monoxide gas is used up in 15 seconds. So that's going to be the rate of disappearance of carbon monoxide gas. But if you look at this reaction, you'll see that the hydrogen will actually be used up faster than the carbon monoxide because there's a 2. For every 2 moles of hydrogen gas being consumed, only 1 mole of carbon monoxide will be used. So we're just going to do a basic stoichiometry calculation here. So if we have 4.5 moles of CO, and we're going to multiply it by 1 mole of CO for every 2 mole of H2. So that's going to be equal to 9 moles of hydrogen gas. And we know that this is all happening within 15 seconds. So 9 moles of hydrogen gas is being consumed in 15 seconds. And this is equal to 0.60 moles per second. And that's going to be the rate of disappearance of hydrogen. All right, now let's consider the factors affecting reaction rates. Okay, so the first one being the nature of reactants. So what this means is in a reaction where the reactants have more or stronger bonds, it's going to take longer to break all these bonds in order to form your products. So therefore you'd have a slower reaction rate. So let's consider this example reaction here. And I drew out the two of the reactants for you, C2O4 2- and MnO4-. So as you can see, there are many bonds that need to be broken. And then compared to like a simple reaction where only like 2 or 3 bonds need to be broken, this is going to happen relatively slower because of all the bonds that need to be broken in order to form products. Okay. So next is concentration. So if you increase concentration, your rate of reaction will increase. And this is because in a confined space, like a fixed container, if you have more particles in there, then there's going to be more frequent collisions. And more frequent collisions mean that you have more successful collisions, which then lead to reactants turning into products. So looking at this example here, I have two beakers, and I'm trying to react the blue dots with the red dots. So on the left side, you can see I have a very high concentration of both blue and red dots. So what's going to happen is there's going to be a lot of frequent collisions. But if we look at the one on the right side, it's much lower in concentration. There are less blue dots and there's less red dots in that same amount of space. So looking at this, we know that on the right side, there'll be way less collisions than the left side. So the left side will have a higher reaction rate. Okay, next we have surface area. This only applies to heterogeneous reactions. So what heterogeneous reaction means is that you're reacting things of different states of matter. So that could be like a solid or a liquid, or a solid and a gas, or two liquids that don't dissolve in each other. And the opposite would be homogeneous, where you're reacting two things of the same state, like liquid, liquid, gas, gas. Yeah, so surface area only applies to heterogeneous reactions, such as if you have a solid and you're putting it into a liquid. So why does increasing surface area also increase the rate of reaction? Well, think of this. If you have your solid and you're reacting with a liquid, you can only really react the amount of solid that's actually being exposed to the liquid, right? So if you have a higher surface area, you could do this by like maybe chopping your solid up or like turning into a powder. Then you're actually exposing more of the reactants to each other at the same amount of time. So similar to the previous example, this will lead to more collisions, which then mean more successful collisions, and then you'll have your reaction. Okay, next is pressure. So we're going to go back to the screen here. If you look at this formula, the ideal gas law, PV equals nRT, let's say we keep the number of moles and the temperature constant. Then we can see that pressure and volume are inversely proportional. So when pressure goes up, volume has to go down, and vice versa. So in order to increase pressure, you have to decrease volume. So you're going to take the gas and you squish it into a smaller space. And then similar to concentration, now you have a higher concentration of gases, which means you'll have more frequent collisions and then more frequent successful collisions. So you have a higher reaction rate if you increase the pressure. Okay, next is temperature. So temperature can be defined as the average kinetic energy. So when you increase temperature, then the particles will have a higher average kinetic energy, which means they would collide faster and with more force or with more energy. So they're going to hit each other harder, and this would also cause more frequent and successful collisions. Okay, finally, we have catalysts or enzymes in biology. And what this does is it speeds up a reaction by lowering the activation energy. And I'll touch on that a little bit more later. All right, now we're going to talk about rate law. So what this is a way to calculate the rate of a reaction at different concentrations. But in order to do that, we need to find three things. We got to find the K, which is the rate constant. And then here in this example, you see A and B in the exponents. That's called the reaction order. And this is simply how much does that concentration of that species affect the reaction rate. Does it affect it like by 2 times, by 3 times, or maybe it doesn't affect the rate at all. So that's what these exponents are. So I won't touch on the theory behind it because it's too complicated, but I'll show you how to do some different problems with this. Okay, let's look at this example here. So this is a reaction between IO3- and HSO3-. And it gives us 3 different trials with 3 different initial reaction rates. And then table of their different concentrations. So let's start by looking at the general form of this rate. So rate is equal to, you have your K, which is your rate constant. You have concentration of IO3 minus, and that's going to be raised to the power of, let's say, A, and that's going to be the order of that reactant. And then we have concentration of HSO3 minus, and then B. So what we're trying to do is trying to solve for K, A, and B so that we can predict any future reactions, like the rate of these future reactions. So how do we do that using this table of values? If we look at any one of these rows here, we would see that it gives us the rate and the two concentrations. So that's basically what we need to fill in this, this rate law here, except we're missing the K and A and B. So how do we use this information to solve for our variables? So let's say we had our first rate, let's just call it rate 1, is equal to the constant times concentration of IO3 minus A, HSO3 minus B. Okay, and then let's say we're going to divide this whole equation by our second rate. So we have another rate, and these are our concentrations, which we don't know. Okay, so let's say that in these two reaction rates, that the concentration of HSO3 minus is constant. Okay, let's say they do not change, they're the exact same. So if we divide these two equations, these would cancel out, the K's would cancel out, and then what we're left with is rate 1 over rate 2 is equal to the first concentration of IO3 minus raised to the power of A over the second concentration of IO3 minus raised to the power of A. So like that, we can compare the rates and the concentrations, and now we can solve for A. So let's try doing this. So looking at this table of values, we'll try to find two trials where there's a constant concentration. So if we look at trial 1 and 2, we can see that HSO3 minus, the concentration is the same. So if we wrote it out, it would cancel. So let's try that. So our first rate is 1.60. It's equal to the concentration of IO3 minus, which is going to be 4 to the power of A, times the concentration of HSO3 minus, which is 6 to the power of B. And we got to make sure to multiply it by the rate constant. Okay, now we're dividing this whole expression by our second trial, which is going to be 0.8 as the rate is equal to K times concentration of IO3 minus, which is going to be 2 to the power of A, and then our concentration of HSO3 minus is going to still be 6 to the power of B. Okay, and we'll divide them. So now our 6 to the power of B will cancel out, as well as our K. So now what we have now is 1.60 divided by 0.80 is equal to 4 divided by 2 to the A. And what this gives us is 2 is equal to 2 to the A. And now we know that A is equal to 1. Okay, so that's the first step. Now we have to solve for B, and then we can solve for K. So let's solve for B. Let's go back to our table here. Let's look for two trials where the other concentration is constant. So we look at trial 2 and 3, we can see that concentration of IO3 minus is constant, whereas the other one changes. So let's use this. Let's write trial 2 first. So 0.80 is our rate, is going to be equal to K times our concentration of IO3 minus, which is 2 to the power of A, times concentration of HSO3 minus, which is 6 to the power of B. And then if we do the same thing for the third trial, we'll have our expression. And this time the concentration of HSO3 minus is 3 to the power of B. Okay, let's divide them. We know that K cancels, and this time the concentration of IO3 minus will cancel because they're the same. And now we have 0.80 over 0.20 is equal to 6 over 3 to the power of B. And then this gives us 4 is equal to 2 to the B. And now we know B is equal to 2 because 2 squared is 4. Okay, so now we solve for A and we solve for B. And now we just need to solve for K. So how do we do that? We look back to our rate expression here. We have the rate, it's given to us. We have the concentration of both of the reactants. And then we have A and we have B. So all we have to do is do some basic algebra and we can find K. So we can actually just pick any of these trials. So I'll just pick trial 1. Okay, so trial 1, we have our rate is 1.60 is equal to K. And then we have our first concentration. And this time we know what A is. We know A is 1, so it's to the power of 1. And then the next concentration, just 6. And we know the B is 2, so it's going to be raised to the power of 2. And now we just solve for K. So K is equal to 1.60 divided by 4 times 36. And plugging into the calculator, we get 0.011. Okay, so now we solve for the value of K, but we don't have the units down. So let's try to find what the units are. So how do we find K? What we did was we divided the rate by 2 concentrations, and the second concentration is squared. So let's look at our units. So for our rate, it says it's in millimoles per liters per second. So let's write that out. Millimoles per liter times second. And then we're dividing it by our concentration. And we're dividing it by concentration 3 times because we have 1 here and 2 concentrations there because it's squared. So we're dividing it by our concentration, which is in millimole per liter cubed. And we can do the math here. It's going to become millimole per liter times second times liter cubed over millimole cubed. And then we can see that this cancels with this, which becomes liters squared. This millimole cancels out this millimole, becomes millimole squared. So what's left is liters squared over millimole squared times second. So our final rate constant would be 0.011 liters squared per millimole squared per second. So that's our K. And putting it all together, we have our new rate law. So rate is equal to 0.011 liters squared per millimole squared per second. And then we have our concentration of IO3 minus to the power of 1, and then multiplied by concentration of HSO3 minus to the power of 2. And that is our completed rate law. We solved for K, solved for our 2 reaction orders. And now what we can do is we can plug in any concentration for our two species and we can calculate the rate. Okay, now let's talk about activation energy. So in any reaction, a particle must have sufficient activation energy for the reaction to actually proceed. So remember when I said temperature affects reaction rate? I said that increasing temperature increases the amount of collisions, which means more successful collisions, which means a higher rate. While that is true, a bigger factor that explains why temperature increases reaction rate is because temperature is actually only the average kinetic energy. You can't say that a substance at the same temperature, all of its particles have the same kinetic energy. The temperature is just the average. So if we look at this chart, this graph here, you can see that their kinetic energy is actually distributed. And in reality, only actually a small percent of them have enough activation energy to proceed. So that's why if we increase the temperature, which is also known as the average kinetic energy, then you would have more molecules with sufficient activation energy. So then you'd have a greater reaction rate. Now let's talk about reaction mechanisms. So we know that for a reaction to occur, particles have to collide with enough activation energy to overcome that activation energy barrier and in the right orientation. But if you think about it, it's actually really unlikely for two particles to collide in the correct orientation and with enough activation energy for the reaction to proceed. So the reaction mechanism theory is that in order for this overall reaction to actually occur, you need a bunch of intermediate steps which are more likely to occur. So looking at this example right here, our overall reaction is 2H2 plus O2 gives you 2H2O. Now, here's a possible mechanism for how this could have happened. So you start with H2 plus O2, which gives you water and just O. And then the second step is H2 plus that O that was just made, and then giving you water. So, and the first step is slow, which is actually known as the rate determining step. So the slow step actually determines the rate because it's the slowest, and all the other steps have to wait for that one step to be completed before they can proceed. So in this example, we see that this one oxygen is being made in the first step, and it's being consumed in the second step. So as soon as it's being made, it's being consumed right away. So what we can do is we can actually cancel that out from the overall reaction. So that's what's known as a reaction intermediate. It's not in the reactants or the products of the overall reaction. So after canceling that out, we can find the overall reaction. So we see we have two H2s. So we have 2H2 plus our 1O2, which gives us our two waters because we have 1 and 2. And if you see, these are the same, the overall reaction. So that's a reaction mechanism. Let's look at this potential energy graph. So what we have is potential energy over, time or reaction progress. So on the left here, we have our reactants, and on the right, we have our products. And if you see this bump, this is actually our activation energy. So our potential energy has to go up, and our reactants need to overcome this barrier in order to become products. So let's call it activation energy. Okay, and if we look at the difference between the potential energy in our reactants and products, that's going to be our delta H. So that's our delta H, our enthalpy change. And as you can see here, it actually goes down. So that means this reaction is exothermic. And what catalysts do is it provides a different path for this reaction to take place, such as something like this. As you can see, we have more steps, but they're lower in activation energy, so it's easier to overcome. So that actually increases the reaction rate. One thing also, in reaction mechanisms, you can have multiple steps. And if you represent it on a graph like this, each step is actually one bump. So let's say you have a 3-step reaction mechanism. It would look something like this. Okay, finally, let's talk about catalysts in reaction mechanisms. So looking at this mechanism here, we can see we have reactants, we have products, we have intermediates, and then we have our catalysts. So first, let's identify our intermediates. So that's what's being made in one step and being consumed in a later step. And let's cancel them out. So first I can see we have a ClOH on this side and on this side too. So I know that as it's being made in the first step, it's being consumed in the second step. So that's going to be our intermediate. That's going to be one of them. So I'm going to label it as I. I'm going to cancel them out. Okay, next I see that our OH minus here is being produced and then being used up in the third step. So that's also an intermediate. Okay, and finally we have our IOH here and here. It's being created in the second step and then immediately used up in the third step. So that's our intermediate. Okay, now looking at this, we canceled out all the intermediates. So what we're left with are reactants, products, and catalysts. So how do we identify the catalysts? We know that the reactants are everything on the left side and the products are everything on the right side. How about catalysts? So catalysts, they're consumed in one step and then they're reproduced in another step. So looking at this, we see that our H2O here, it's being consumed in the first step, but it's being made again in our last step. So we know that the H2O is a catalyst in this mechanism. So that'll be it for my first video. Hopefully it was easy to understand, and you can leave any questions or comments in the comments. Thank you.